Okay, this video is not going well so far. This is my third try at it. The first time the video was all messed up. The second time the audio was off somehow and I didn't realize it until I recorded the whole thing. And the third time I think I've got it all figured out here. Also apologize, I've got a little bit of a cough today, so sorry if I cough during this. We're going to walk through a sample of some of the calculations here that you need to do for homework 2. So we've got these kind of input baseline data that you're given, where you've got the ground reaction force characteristics here, and then the kinematics of the hip and the knee and the ankle and the center of pressure there. And from these data, we want to calculate our index of performance, which is just the vertical magnitude of that force. And also then we want to calculate the index of efficiency, which is the ratio of that force divided by the torques or moments at these joints that were used to produce that force. So to do that, we then have to calculate the torques that are produced at those joints, at the hip, knee, and the ankle, in response to that ground reaction force. So let's step through how we might do that in Microsoft Excel here. So I'll make a new sheet, and let's zoom in a little bit to see a little better here. Okay, so I've got these inputs here that I'm going to copy over from my sheet. And we're going to have the magnitude of the force, and that's got units of newtons. We're going to have the angle of that force, and that's going to have units of radians. And then we're going to have the x coordinate for the hip, x coordinate for the knee, and x coordinate for the ankle, and the x coordinate for the center of pressure. And then we'll also have y coordinates for all those things. Y for the hip, y for the knee, y for the ankle, y for center pressure. And then my outputs that I'm going to calculate are going to be the vertical component of that force, the horizontal component of that force, the moments that I produce at those joints, oops, that's moment at the knee, and then the sum of those three moments, which we're just going to call M there. Okay, and then I'm going to calculate all these things with 4 different conditions. I've got my baseline condition, which is just the vertical force and the moments associated with this kind of baseline, default jumping condition you were given. And then I've got the stronger condition, where the magnitude of the force gets bigger, but nothing else changes. And then you've got the technique condition, where the direction of the force changes, but the magnitude of it doesn't. And then you've got the both condition, where you change the magnitude of the force and the direction of the force. So the combination of both the stronger condition and the technique condition at the same time. Okay. So first thing we want to do is copy over these inputs for that baseline condition. So the force is 924 newtons, the angle is 82 degrees, so 924. And 82, when I'm doing trigonometric functions like sine and cosine and stuff like that, I'm going to want the units of the angle to be in radians instead of degrees. So I'm going to take that 82 degrees and multiply it by pi and divide by 180 to get it in radians there. And then I'm going to copy over my x-coordinate for the hip, which was 0. X-coordinate for the knee was 0.42 meters. And x-coordinate for the ankle was 0.14 meters. And x-coordinate for the center of pressure was 0.21 meters. Okay. And then get my y-coordinates there. Y-coordinate for the hip was 0.63 meters. Y for the knee is 0.49. Y for the ankle was 0.14. And center pressure is always on the ground, so that is 0. Okay. Now you'll see when I get down here that when I'm calculating the joint moments, I'm doing it at the hip, and then the knee, and then the ankle. So hip at the top, knee in the middle, ankle at the bottom. The calculations are going to be assisted by, or you'll save yourself some time if whatever order you do down here, you position all the x coordinates of those joints in that same order here, and then all the y coordinates in that same order here, right? So if it's hip and then knee and then ankle for the moments, also do hip and then knee and then ankle here for the x coordinates, hip and then knee and then ankle there for the y coordinates. And you'll see why that's helpful as I go through this calculation here. So first thing we want to do is get the vertical force. That's our index of performance. And that's pretty easy. That's just taking the magnitude of the force times the sine of the angle of the force. Okay. And then I don't need the horizontal component of that force as an index of the performance. It's not an index of the performance, but I do need the horizontal part of that force in order to calculate these joint moments. So I'll go ahead and get that too. That's going to be the overall magnitude times the cosine of that angle. Okay. Now for the joint moments, for any one of these joint moments, we'll just start with the hip here. I'm going to take these two forces, and let's just start with the vertical force here. I'm going to take that vertical force times its moment arm to the hip, and that's going to give me the torque at the hip joint that's associated with that vertical ground reaction force. Okay? The horizontal part of that ground reaction force also is associated with the torque at the hip joint, so I'm then going to take that torque that I associated with the vertical force and add to it the torque that I associated with the horizontal force. Okay? So for each one of these forces, the vertical force and the horizontal force, I'm going to take each one of them times their respective moment arms to the hip, sum those two resulting torques together, and that's my hip torque here. Okay? So let's start with my vertical force, so my vertical ground reaction force. Its moment arm is going to be the horizontal coordinate of the center of pressure, so xp, minus the horizontal coordinate of the hip, xh, times that vertical force. Okay, so that's the torque at the hip joint that's associated with the vertical ground reaction force. I'm going to add to that the moment arm for the horizontal ground reaction force, which is the vertical coordinate of the center of pressure, minus the vertical coordinate for the hip, times that horizontal ground reaction force. Okay. Now, notice here in my equation, it's got everything color-coded here for me. My vertical ground reaction force, cell B13 there, its moment arm there is a difference in vertical coordinates. The difference between difference in horizontal coordinates. It's a vertical force in cell B13, Fy, and its moment arm is a difference in horizontal coordinates. The horizontal location of the center of pressure, or location of the force itself in B7, minus in B4 the horizontal position of the hip, or the position of the actual joint that we're calculating the torque about. Okay. Then similarly here, when I'm dealing with that horizontal force in B14, its moment arm is a difference in vertical coordinates, the vertical coordinate of the center of pressure minus the vertical coordinate of the joint that I'm calculating the torque at. Okay, so that's kind of your check on if you're doing this right. You can step through the calculations and use that as a check for if you have this set up right. You should be multiplying the vertical force by a difference in horizontal coordinates. And which horizontal coordinates? Well, specifically, it should be the location of the force minus the location of the joint that you're calculating the torque at. So take that vertical force and multiply it by those horizontal coordinates, and then take that horizontal force and multiply it by the same vertical coordinates, those same two things, the location of the force and the location of the joint that you're calculating the torque at. So if I do that, I get about 111 Newton meters of torque there. Okay, then I want to just copy paste that down here for my knee. I don't want to repeat all that typing in. I want to just reuse this formula here if I can. And that kind of works, but kind of doesn't. That's not the right torque there for the knee. Notice when I double click on my cell here, it color codes everything I'm working with. So it's got cell B4 and 7 and 8 and 11 and the forces there. If I double click on the knee moment calculation there, because I shifted that down by one cell from the hip moment calculation there, all it did was shift all those cells that it's doing the calculation from down by one cell. And that's not what we want, right? I want it to calculate this knee moment using these same two forces and these same coordinates for the center of pressure. I just want it to use these knee position coordinates here instead of those hip coordinates, right? And then similarly, when I copy it down to the ankle there, it's still going to be grabbing, or I still want it to grab those same ground reaction forces, and I still want it to grab those same center pressure coordinates, but I want it to use the ankle coordinates instead of the hip or the knee coordinates. Right? So let's go back up to my hip here, and let's tell it, hey, I want you to always use these two forces and these two locations for that force, but I then want you to keep the coordinate of the joint. I want you to kind of keep that rolling, keep that dependent on which cell or which torque I'm calculating here. So my forces, I'm going to put a dollar sign in front of the B and a dollar sign in front of the 13. And then I'll put a dollar sign in front of the B and a dollar sign in front of the 14. So that's going to tell it, when I take this cell here and copy and paste it somewhere, it's going to tell it, even though you moved me, I want you to still go and grab whatever data is in these same two cells here that I labeled with those dollar signs. The dollar sign in front of the B is saying always go to column B, and the dollar sign in front of the number is saying always go to that specific row to get those numbers. Okay? Now we're still not quite there. That 129 is still not quite right because again I always want it to reference here the center of pressure, which is B7, so we'll give that dollar signs, and B11, so we'll give that dollar signs. Okay? So now when I copy paste this down one cell, it's going to move the horizontal hip here down to the horizontal knee and the vertical hip there down to the vertical knee, but it's going to keep referencing those same two forces and those same two center pressure coordinates. So I should get the right knee moment if I do that calculation. And that's I did this ahead of time, so I know what the results are, but that's the knee moment that I should be expecting there, about negative 255 Newton meters. And then if I copy that down again for the ankle, I should get the expected ankle moment there, which is about 46 Newton meters. And we don't need umpteen digits of significance here, so we're going to make that a little bit more agreeable. We don't really need any units there. We can just leave that off. So just have it in whole units there, so no significant digits needed. Okay, last thing I'm going to do here, actually second to last thing, is I'm going to sum up these moments together. And when you're summing these three moments, adding the hip and the knee and the ankle together, you don't just want to add them directly like this, because one of them's got a negative sign. This is because the way that I defined these calculations, I did it with kind of a, I'll call it an engineering definition of the torques at the joints, where I called counterclockwise always positive and clockwise always negative. Physiologically or biomechanically, that gets us into some trouble because an extensor moment or an extension moment at the knee and at the joint, which is what we have when we're jumping, we're extending the hip, extending the knee, extending the ankle. That has an opposite sign at the knee than it does at the hip and the ankle, right? So I'm actually, if I include that negative sign and I sum them up, I'm actually making the total torque there look smaller than it really is physiologically, because that knee has a negative sign in terms of its direction, but it doesn't have a negative sign in the sense that these are all extensor moments, all pressing into the ground and pushing the center of mass or encouraging the center of mass to accelerate upward. So when we do that summation, we actually want to sum up the absolute values of those three torques, which says just ignore the negative sign if it's on there. So I'm going to take the absolute value of the hip torque plus the absolute value of the knee torque plus the absolute value of the ankle torque. And that's my total sum of the torques there. And then lastly, my index of efficiency, I'm just going to take that vertical force and divide it by that sum of those moments. I get about 2.2 there. Okay, and there we don't need umpteen different significant digits either. We can stick with just 2 there is probably good. Okay, now the nice thing about setting it up this way is now here's my kind of baseline condition that's just going to form my basis for comparison here. In the stronger condition, the magnitude of the force gets 5% bigger, so I can just take that times 1.05, and everything else there stays the same. Okay. And the nice thing is I should be able to just copy paste these calculations here over one cell, and it'll just automatically get me what I want. Okay. Now, it sort of got me what I wanted. It worked for the forces. You can see here, it took the new force times the sine of the new angle. It's actually the same as the old angle. And here, new force times sine of the or cosine of the angle. But for my torques, it got exactly the same torques as my baseline condition, in the stronger condition. That just kind of intuitively seems unlikely, right? That the torques like wouldn't change at all. And let's double click on the hip torque calculation here for the stronger condition and just see what happened there. So notice here it's still referencing a lot of the data from the baseline condition. Doesn't really matter that it's grabbing the old centers of pressure. Those are the same there. In the baseline versus the stronger condition, but the forces changed in the baseline and the stronger condition. It's not grabbing those right forces. So I want to go back here to my hip condition, and with my dollar signs here, I want to tell it, okay, you're always going to go to, for example, row 7 to get that center pressure x coordinate, but I want you to grab whatever column is the current column of the condition I'm working with. So let's get rid of that dollar sign in front of the B on B7 there. And same idea for the forces. I want it to go and grab the force that's within whatever column I'm working with, so I won't make that static there. And same deal there for my vertical center of pressure in B11. I want that to be C11 when I copy it over, and same deal here for my force. I want it to be B14, or my horizontal force. I want it to be B14 when I'm doing baseline. I want it to be C14 when I'm doing stronger. Okay. So that shouldn't have affected what I got on my hip in baseline, and it didn't. Let's just copy it down here to knee on baseline to see if that stays the same. And it does. Down there for ankle, and it does. And then let's copy that over here for the stronger condition and see what we get. And there we got a little bit different torques. So there's that. Now there we can have some confidence that, okay, it's actually maybe using the right things. And if we double click on the hip here, then we can see it is indeed using the right data that we want it to have there. Okay. Okay, so that is your sample calculation here for the calculations of the outputs or the results here for the performance or index of performance in homework 2, which is that vertical force, and then the index of efficiency, which is the ratio between that force and the torques used to produce that force. In all of these, if you're doing it right, you should get forces that are on the order of 900-ish newtons or so, and you should get ratios here that are on the order of like 2 point something. So if you're getting, values here way different from 900, like if you're getting 100 or 8,000 or whatever, something's wrong. And down here, if you're getting something that's vastly different from like the number 2, something's wrong there. If you're getting like 1 or 15 or whatever, it's 2 point something is what you should be looking there. It shouldn't be vastly different from that. So this is a nice way to set it up, because now in the technique condition, all I got to do is change the inputs up here, and I can just copy paste everything else. Like it's the same force, but now my angle got 5% bigger, 5% more vertical. Nothing else changed. And then you can just copy paste over these calculations there and get your results for that technique condition. Then for the both condition, they both increase by 5%. This other stuff stays the same, and then you can copy paste over your calculations there and get your two outputs in bold there. So here you should be looking at, does the performance change, and then does the efficiency I was using to produce that performance change? And you should see some differences there between these different conditions. For example, you can see in the stronger condition, yeah, the performance increased by a good chunk, but the efficiency was not affected. It was not that the efficiency got worse, but it just wasn't affected by that intervention. So just the strengthening intervention was effective for performance, but wasn't effective for efficiency. And you still see that both in the technique intervention and in the combined intervention there. Okay, that is my suggestion for how to go about this, and hopefully this is helpful to y'all for homework 2.